Hello, everyone, and welcome to this free webinar series presented by WePast. My name is Christina Ruiz, and I will be your moderator this evening. Throughout the webinar, we will stop the presentation to review. There will be 5 multiple-choice poll questions, which you will be able to answer in the sidebar. Please go ahead and answer these questions as they come up. You will have about 1 minute to answer the question before we go over the answer. During the webinar, please feel free to use the chat window to ask questions and discuss the topic. We will take time after the presentation to answer these. This and other recorded webinars will be available to WePast subscribers. Register through WePast.com to become a subscriber. Tonight's topic is titled, What You Need to Know About Medical Linacs Part 2, presented by Timothy J. Waldron, MS from the Medical Physics Group and Radiation Oncology Department at the University of Iowa Hospital and Clinics. Thank you for joining us, Tim.
Well, thanks for that great introduction. So tonight we're going to be talking about medical Linacs. This is part 2 in a series of 2. It's the second hour. My employer likes me to disclose potential conflicts of interest, so I own stock in the companies shown on this slide. However, I'm not getting any funding from any of these companies right now other than that stock ownership. Tonight's learning objectives are going to be to become familiar with the basic principles and relative clinical aspects of electron accelerator, really the technology downstream from beam formation. In the first hour, we talked about basically generating an electron beam, electrons, accelerator, bending magnet. I'm going to briefly, and I mean really briefly, recap the high points from the last lecture. That's going to involve talking a bit about bending magnets, and then we'll move on to a discussion of what we mean when we talk about electron energy. Thereafter, we'll talk about some generic treatment head layouts. What does the beam encounter once it leaves the bending magnet? We'll cover X-ray production, in which, of course, the target is the important part there. Photon beam uniformity and how we manage it. The beam monitor or ion chamber, which, of course, tells us how much dose we're giving eventually. How do we shape or collimate the photon beam? What are some of the effects of beam steering? And then what about electron beam uniformity and collimation? We'll then sort of shift gears one more time and talk about head leakage and wedges and their effects on beams. So looking at the last lecture, we covered the items that are bright in this slide. And of course, here's my generic medical Linac. Most medical Linacs contain each of the items shown in this cartoon. Particle injection, electrons in our case. We have an accelerating structure where the electrons are accelerated. Our accelerating potential is microwaves or electromagnetic waves, which we're getting from our RF radio frequency system. This, in turn, is powered by a specialized high-voltage power supply, often called the modulator. The electron beam, in most cases, enters a bending magnet system. The role of the bending magnet system is to effectively act as a band-pass energy filter and select a narrow range of energies from the intrinsic electron energy, which is what we call the electron spectrum prior to entering the bending magnet. So for today's lecture, we're going to be covering the items that are bright. We'll briefly talk about what's happening in a bending magnet, just to have a little overlap from last time. We will talk about targets or production of X-rays. We'll then talk about methods of making the beams uniform in intensity, dosimetry and dosimetry devices internal to the machine, and then collimation or beam shaping. In each case, we'll be doing this both for photons and electrons. I will be jumping back and forth a little bit between photon and electron when it comes to each of these items. So here's the very brief recap of the previous lecture. I'm going to try and cover all of it in just 2 slides. The first thing we talked about was the electron injector or gun, and this has 3 fundamental functions in a medical linear accelerator. It is the source of electrons, and of course they are generally acquired through thermionic emission. It imparts some initial velocity to the electrons to get them into the accelerator so they can be accelerated. It also provides a means of turning the beam on and off. The accelerating structure itself, sometimes referred to as the accelerating guide or accelerator, is a series of coaxially coupled resonant cavities. These resonant cavities give us an environment that allows electromagnetic waves to transverse or propagate through the structure in transverse magnetic mode. What that means is that the electric field component of the microwaves is in the same direction as the axis of the accelerator. This means that charges present will be accelerated either forwards or backwards. There are 2 types of accelerating structures in medical use. The first one is the traveling wave accelerator. These tend to be physically longer and are less complicated from a microwave design perspective or RF design perspective. The other type is the standing wave accelerator. These are more compact, but they also require a more sophisticated RF system. We also covered briefly how we control energy in these systems. How do we change the energy of the electrons leaving the accelerator? And what really controls the energy that the electrons are acquiring as they're being accelerated is the RF power in each cavity. So in general, what we're really talking about are techniques to control the RF power in each cavity and subsequently changing the electron beam energy. And so one way we can do that is by changing the amount of RF power that we provide into the entire structure. This will increase or decrease the acceleration of the electrons. We can change the effective length of the structure if we happen to have a standing wave accelerator by using an energy switch, which effectively turns some length of the structure or other into a drift tube. Another way we control power is by what's called beam loading, and that is because a given amount of RF power does not provide us an unlimited work function. We cannot accelerate an infinite amount of electron current with a given amount of RF power. Therefore, by loading or unloading the beam, the accelerating potential with higher or lower electron current, we can raise or lower the final energy of the electron beam as it's leaving the accelerator. This is also known as the intrinsic energy. We also talked very briefly about RF systems. There are 2 basic kinds of sources of microwaves in use. The first one is the klystron. The klystron is an amplifier. It amplifies microwaves through a process of velocity modulation. Internally, it has an electron beam. This electron beam is modulated by the presence of a buncher cavity into which we're feeding a relatively low power microwave signal. This modulated beam then couples its energy out of a second cavity that we call a catcher cavity. The catcher cavity couples the now space and time reoriented electron beam out through a waveguide to eventually to the accelerator. So velocity modulation is the mechanism by which a klystron amplifies microwaves. And as I said, it's an amplifier and it requires an input. The other source of microwaves used in medical accelerators is the magnetron. A magnetron is generally set up as an oscillator in these machines, and it is composed of a series of resonant cavities arranged in a circular anode structure with a coaxial central cathode. Electrons emitted by the cathode are caused to circulate past the anode cavities by a magnetic field. Like the klystron, the electrons passing the cavities exchange energy with the cavities. This alternately excites the cavities very much like the buncher and the catcher cavities in the klystron. This energy exchange creates very large electromagnetic fields within the cavities that can then be subsequently combined and coupled out of the magnetron into a waveguide. of course, we need some high voltage to operate these devices with, and we have what is really just a high voltage power supply, often called a modulator. Excuse me. The modulator generally has an output of between about 50 and 120 kilovolts peak at anywhere between 100 and 120 amps peak. And what is important is that we have a pulse width of about 5 microseconds and a pulse repetition frequency of 200 to 400 pulses per second. Now, these are kind of soft numbers. There's some variation with manufacture and design, but they're generally within this range. The last item we talked about was the bending magnet. The bending magnet functionally is selecting a narrow range of electron energies from the intrinsic energy spectrum exiting the accelerator. And now we're back where we left off at the end of part 1. So to recite what I said earlier, from this point on, we're in the bending magnet, and I will show 2 bending magnet designs. Thereafter, we will be essentially following the path of the energy or the beam out of the accelerator through either the flattening system for photons, the flattening system for electrons, collimation for photons and electrons, and dosimetry for photons and electrons. So let's get going. And a reminder here that not all medical Linacs have bending magnets. If we are talking about a machine that happens to be called a tomotherapy unit or a CyberKnife unit or a Mobitron unit, there is no bending magnet at the exit of the accelerator. The accelerators tend to be short in length and are oftentimes just a single energy. And frequently, if they're producing photons, that target is going to be welded on the end of the accelerator. Of course, because there's no bending magnet, now our control of energy spectrum is going to depend largely upon the intrinsic energy of the electron beam within the accelerator, and then engineering issues regarding target design and flattening filter design. And I've threatened a number of times now to review bending magnets, and we'll begin that review with this slide. We have what we can call the Lorentz relationship, which says that the force on an electron in a dipole magnetic field is a function of the electric field, the velocity of the electron, and the magnetic field, as well as the charge. Of course, the charge is known if I'm talking about an electron, but it applies for any charged particle. And basically what we're talking about is that an electron with some velocity in the presence of a magnetic field will tend to take a curved path where the curve is proportional to both the magnetic field and the initial velocity of the electron. And the radius of curvature of that curved field is shown here, and it is a function of the magnetic field strength, the charge, the mass, and the velocity of the electron. We could also say that this is a function of the magnetic field strength and the energy of the electron. To put it very simply, higher energy electrons are bent less or through a larger radius in a given magnetic field, and lower energy electrons are bent more or through a smaller radius in a given magnetic field. So if I happen to have a Varian machine or a Siemens machine, I'm generally going to have what's called a 270-degree bending magnet, and generally on these machines, the electron beam is shown entering horizontally from the left here. When it enters the first portion of the magnetic field, it is spread out. Higher energy beams are the red path, lower energy beams are the green path, and the selected energy, which I'm showing as E0 here, is the blue path. At the greatly spread out portion of the trajectory through the bending magnet, we put a pair of energy slits, and those energy slits are going to intercept any electrons whose energy is greater than what I'm calling E high here, or lower than what I'm calling E low here, and in general that is a plus minus 3% slit. In other words, electrons with energies within plus and minus 3% of this central E naught will make it through the slits. Outside of that range, they will be stopped by the slits and essentially make hot water. Of course, the energy slits have to be cooled. Otherwise, we would burn them up or melt them or something. In the rest of the field, the electron beam is generally refocused on a point. Usually this point is where we will later put the target or the exit window of the accelerator, depending upon the design. We don't have to put all those bending magnets all in a 270-degree loop. We can take that same set of bends and rearrange them. So we bend first down and then up and then down again. If we consider that the Electa design, the accelerator is already sitting at some angle, and we combine the bends of the angles, we still come up with a number that is 220-something degrees. I mean, the exact value doesn't matter terribly. And again, we put a set of slits where we want to chop off, if you will, the highest and lowest beam energies. And on the Electa system, I'd like to draw your attention to this portion here of the pink vacuum chamber. There are really two exit points, and I'll talk more about this later. There is a bellows over here on the left. This entire pink section can slide left and right in this picture in order to put the beam focal spot at either this window here or this window here. So I've used the word electron beam energy repeatedly. And I've also said that the bending magnet selects a narrow range of electrons from the intrinsic energy spectrum. Well, what energy are we talking about? I mean, when we say energy, do we mean an energy? Do we mean a spectrum? The word energy can mean a lot of things. And so what I'd like to do is spend a couple of slides just sort of talking about what we mean by different energy designations. So here's a little table. Symbols are on the left, meanings are on the right. These meanings are largely taken from a document known as ICRU 35. It is a guidance document on electron dosimetry, sort of in general, and it defines most of these terms. We've already talked about kinetic energy of electrons, of course. Generally, when we talk about energy of electrons, we mean the kinetic energy. So, of course, E bar is mean energy. Intrinsic accelerator energy, usually E sub n is the intrinsic energy. E sub a refers to, it sort of means the energy still in the accelerator, but it often refers to the energy after the bending magnet rather than before the bending magnet. Usually E sub n refers to the intrinsic energy specifically prior to the bending magnet. The initial electron energy refers to the energy as it is leaving the vacuum of the accelerator. So we're now beyond the window. We've exited the bending magnet. E max refers to maximum energy, regardless of whether we're in the accelerator or out of the accelerator. E naught, now E naught, E sub p, and E sub z have very specific meanings dosimetrically, and of course these are clinical terms. E naught refers to the electron energy at the surface of usually a water phantom when we talk about it. E sub p is the most probable energy, and the most probable energy can refer to any one of these energies here so far. And E sub z refers specifically to energy at a given depth. Again, this is a clinical sort of energy designation. ICRU 35 uses gamma to refer to the energy spread. And so in this case, gamma sub A refers to the full width half maximum of the energy spectrum in the accelerator, really in the bending magnet at this point. And of course, normally when we see these designations, we see them combined. Of course, the most probable energy at the surface of a phantom is going to be called EP comma 0. And we can have an EP comma Z and so on and so forth. So they're not always just these designations, but it would take several slides to be exhaustive. So let me show a couple of examples of some electron spectrums and sort of get a sense of how they look and how they change as we manipulate them. So here is a figure I've adapted from Karsmark. Basically, I've copied it and colorized it. This is from the 1993, no longer in print version of the Karsmark and Noonan and Tanabe book. The vertical axis here is relative fluence. The horizontal axis is energy and MeV. This is the intrinsic electron spectrum, which I'm saying is E sub n or E sub a for a 6 or 18 MeV photon beam. So this is the electron energies spectrum in the accelerator that's going to produce either a 6 MeV or an 18 MeV beam. We can see here that for the 6 MeV beam, we have a sharp peak right about at 6 MeV. And the spectrum extends down below 4 MeV and up past 8 MeV. But of course, the effect of the energy slit is going to be limiting that portion of the spectrum which might leave the bending magnet as between these pair of dashed lines. And that's the 3% limits presented by the energy slits in the bending magnet. Over here on the right, we've got the 18 MeV, or the what eventually will be an 18 MeV electron spectrum. And we can see we have a peak at about 18 MeV. And we have some spread. Of course, 3% of 18 MeV is going to be about 3 times the width of 3% at 6 MeV. So these dashed lines are much farther apart. And we can see we're chopping off, just lower energy and higher energy. And really, this is sort of what we're demonstrating with this figure. Now, when we take an electron beam and we load it, recall in the last lecture and earlier in this lecture, I mentioned beam loading. And I said that if we have a particular amount of RF power in the accelerator, we can only accelerate so many electrons at a time to the energy that corresponds to that power level. In other words, for a given power level, there's an optimal loading. So again, this is going to be a set of spectrums. Vertical axis is relative intensity. We could call it fluence quite easily, or relative fluence. The horizontal axis is the energy in MeV, and this one is going to be for a 10 MeV EP0 electron beam. So this would be a clinical 10 MeV beam where the 10 MeV is the most probable energy at the surface of a water phantom or the patient or whatever. So the first thing we're going to look at is the optimally loaded spectrum. And it looks an awful lot like the spectra we saw in the last figures. We've got a peak at 10 MeV. We've got some fall off that extends slightly higher. And then we have a longer tail at lower frequencies. Now, if I take this and I unload it, I either increase the RF power or I decrease the electron fluence. What I'm going to get is I'm going to get the lightly loaded beam. And what you can see here is that the beam spectrum is clearly above 10 MeV. It's also quite spread out. We do have a clear peak, and the representation here is almost as if the area under the curve for this one is the same as this one. These were measured with a magnetometer, probably at the entrance of the bending magnet rather than anywhere else in the machine, and I'll explain why for that in a moment. If we load this beam heavily, we're going to get a spectrum that looks like this. And of course, it's heavily loaded. The energy is much lower. We still have a peak. The shape for the heavily loaded beam looks a lot more like the optimally loaded beam, but it is considerably lower. Again, it may be that we're looking at the same area under the curve, but I'm not sure about that. Of course, once we get past the bending magnet, we're not going to see either one of these because the 3% slit is going to prevent anything above this line or below this line from exiting the machine, which is why when the service engineer is at your clinic and they are quote unquote tuning the beam, what they're doing is loading and unloading the beam in order to have the selected energy passing through the center of the slits in the bending magnet. So it would be set so that we're, in this range here rather than anywhere else. And of course, once we're outside of these two, there's no dose rate indicated on the machine because the beam's not exiting. Here are some spectra from ICRU 35. And here now we're getting into a little bit more exercise of those energy designations, and I'd like to start on the right here. Again, vertical is relative fluence, horizontal is energy in MeV, and now what I'm referring to here is strictly what would be a clinical electron beam. And now we're outside the accelerator, or just at the accelerator window. On the right here in green, I've got EPA. So this is the most probable energy in the accelerator, and I think we're just in the window here, or leaving the machine, or at the window. And you can see we've got a gamma sub A. So gamma sub A refers to the full width half maximum of the distribution. I'm going to say at the accelerator window, or just inside the accelerator window. I've got an Emax value. This is going to be the maximum energy at the accelerator window. So we're going to be near to that 3%. That 3% number is sort of quite wider in this depiction. And then down here at around a third of the maximum value, I've got the EA bar, which is the average energy at the accelerator. If we consider the yellow or golden plot in the middle here, now we're talking about the electron spectrum at the surface, or at the surface of a water phantom or the patient. And so, of course, we've got the same designations here. We've got a gamma sub 0, an EP 0, an E bar 0, an Emax 0, and so on. And what we can see is that just in passing out of the accelerator and through the air between the window and the patient, the energy spectrum has almost doubled in width. And of course, now over here on the left with this blue curve, you can see now we're talking about EPZ, which is the most probable energy at depth, E bar Z, the average energy at depth, E max at depth, and so on. The energy spread is considerably wider than either of the other two in terms of just energy width. So the electron energy spreads out very rapidly when it leaves the vacuum and travels through first air and then mediums such as water. So here's our first question. Christina, are you ready with the question?
Yep. Hello? Can you hear me?
Hello.
All right, I'm ready for the first question. Let me just go ahead and load it. We are going to start the poll here. And for those of you who haven't had a chance to do a poll with us before, I'm just going to give you some brief instructions. So it should be on the left-hand side of your screen. If you can just, everyone, take a moment to answer the questions. And then once you've submitted your answer, we should be able to see how other participants have responded. And in about a minute, we can take a moment to review the question.
And I'm going to go ahead and read the question. So what is the greatest difference between intrinsic and accelerator electron energy spectra, E sub n and E sub a, and the other spectra we talked about, which are the E sub I, E sub naught, and E sub z?
Looks like the answers are coming in.
Yeah, good, good.
All right, Tim, it looks like a fair number of people have had a chance to weigh in on the poll. Would you be able to go over the answer for us?
Sure. Looks like the majority got it right, or at least half. I do try to make my questions somewhat board-like in that 2 of them are silly and 2 of them are difficult, and only one of them is the most correct. So we said, what is the greatest difference between intrinsic and accelerator energy spectra, E sub n and E sub a, as compared to the E sub I, E sub 0, and E sub z. So was it question 1, E sub n and E sub a have much wider full width half maximum than E sub I, E sub 0, and E sub z? And as we saw in the last slide, no, that is not the case. The the energy spread increases immediately as we get out into the world and we start calling it I, E, and Z as opposed to N and A. Is it that all are most probable or peak values and these two are not? Well, no, we saw in the last slide and the slide before that all of these could have a most probable designation. Was it that E sub n and E sub a have much higher average energies than the others? Well, no, really. There's no way to say what their average energy is going to be necessarily. And so that just leaves D. And yes, E sub n and E sub a refer to electron energy spectrum on the vacuum side of the exit window, whereas these other three definitely refer to the electron beam energy after it's left the accelerator and is either in the air at the window or at the surface or at depth. All right, we'll continue now. So now we're in what we generally call a treatment head. I'm going to first talk about a photon beam treatment head, then an electron beam treatment head, then I'm going to jump back to photons, and we're sort of going to be moving back and forth between electrons and photons. So within the treatment head, we have the source. You know, it's the point where our radiation beam is emanating from. For a photon beam, this is generally the target. And then, of course, down here, we have this thing we call isocenter, which is, it's the only place we really know what's going on in the treatment room. And typically, it is 100 centimeters to the source. The line that connects these 2 points is frequently referred to as the beam central axis. And we would like to think that that corresponds to some certain centers of rotation of different parts of the machine, but that is a different lecture. The next thing that the photon beam now might encounter is something called the primary collimator. We always draw pictures with rays of photons leaving the target in one direction, but the reality is we are producing a very forward-peaked photon beam, but there are photons and electrons and particles just shooting everywhere in this picture. So we need something to define the cone of radiation that's going to leave the machine, and this is what the primary collimator does. And you can think of it as a large slab of high-density material. It needs to be high density because we're largely talking about a Compton interaction as a means of interaction. And high Z materials tend to be high density. And so this is generally something made of steel. It needs to be thick enough to attenuate virtually the entire beam. So that means it's going to be 10 or 11 half value thicknesses for the energies we're talking about. And the cone that is defined by the sides of this collimator is going to correspond to the triangle that's going to give us the field width defined at the isocenter that can be made with the machine at a maximum. Usually we're talking about a 12 to 14 degree angle at the top here, the two halves, the full triangle. So it's going to be a cone of whose full diameter corresponds to about around 12 degrees to 14 degrees. The next thing that the beam encounters is going to be the flattener. And what the flattener does, and it's usually a cone-shaped piece of high-density material, and I'll cover it in more detail a little later, it is going to give us a uniform photon intensity over the entire field. Or not. If we have a flattening filter-free beam, there is no flattener in there. For the moment, we're going to leave it in there so we can talk about it. The next thing that the beam is going to encounter in general is going to be some means of measuring the dose rate. What is the centigrade per monitor unit coming out? What are the monitor units that have come out of the machine? Excuse me. And I'm calling it dose rate because it doesn't really measure dose. It measures something that we later on relate to dose rate when we do a calibration of How many centigrade does a monitor unit correspond to? And of course, that is another lecture too. And generally what we're talking about is a transmission ion chamber or two. We'll cover those in detail in a little later. The next thing we're going to have is block collimation. Current machines have different combinations of block and multi-leaf collimation. I'm showing a rather old school presentation here, but they're still out there. We have 4 blocks. Each pair of blocks defines two sides of a rectangle, and the blocks can be moved in order to make rectangular fields. These must also be a large number of half-value thicknesses, and so of course we're going to use high-density materials, tungsten, steel loaded with lead, etc., etc. And we're usually talking ranges of 10 to 14 centimeters in thickness. I'd like to point out that the beam penumbra, which is the beam edge, and we'll mention that a little bit more later, is greatly affected by the direction in which the face of these collimators is oriented. The collimating face of the collimating block must be parallel to a ray line projected from the source to wherever we're sending the beam. And that means that if the collimator is just a block, it has to move in sort of an arc path shown here, right? And so the block face is going to be perpendicular to this arc and parallel to this ray line as it opens and closes. I'd also like to point out that for photon heads, the distal portion of the collimation is in general far from isocenter. Usually the distance from the bottom of the jaws to the isocenter is in the range of 50 to 60 centimeters. An electron beam head, by comparison, and of course we're starting out in photon mode here, the source is going to be the exit window of the accelerator. In other words, we've got a window, usually nickel. One side's vacuum, the other side's the world. The beam will exit that window. Electrons scatter a lot, so we're still going to need the primary collimator to define our cone of radiation. We're going to need something to make the electron beam uniform, but it's not going to be a cone-shaped piece of metal. We'll use some other means to do that. For now, I'm showing 2 thin layers to scatter the beam, and there'll be more detail on that later. We still have the transmission ion chamber. The block collimation might still be present, but it is largely withdrawn for electron beams, and I'm going to remove the one that would move in and out of the picture at this point so that we can show that electrons scatter in air. They scatter a lot in air. And that means that in order to have any kind of beam edge down here at the patient, I need to collimate the beams repeatedly over and over, and the distal component of the collimation must be very near to my isocenter or my patient, and typically that's a 5 centimeter distance. It's usually 95 centimeters to the bottom of the electron collimators. Back to photons, and we'll be sticking with photons for a little while here. I've said the word target a few times. What do I mean by a target? The target is the thing that turns our electron beam into a photon beam. And the way this happens is we place some high Z material in the electron beam. Electrons have an opportunity then to undergo Bremsstrahlung interaction with the nuclei of the material we've placed in there. When that happens, an incident electron is influenced by the net positive charge of the nucleus. This causes it to bend. The bending is a change in acceleration. That indicates a change in energy. Energy must be conserved. Energy is conserved by the emission of a photon whose energy corresponds to the total energy difference of the electron. And I'm explicitly showing total energy here with the rest energies included. Target efficiency. Hopefully, obviously, if we want to have lots of interactions, we want to have a very high Z material as our target. And so if I want to have a very efficient target, I have this formula, which you can find in Con, and that is efficiency in general is 9 times 10 to the minus 10th times Z, where Z is the Z of the target material, and V is the accelerating potential in volts. So if I have 100 electrons at 1 megavolt incident on a tungsten target whose Z is 74, about 7 of those electrons are going to produce X-rays or photons. The other 93 or so are going to produce mostly heat and will be scattered, and so on. So one interesting feature of this is that because of the V here, if I have a 6 MV beam and an 18 MV beam, I'm going to need about 3 times the electrons for my 6 MV beam that I have for my photon MV beam in order to produce the same photon fluence leaving the target. Of course, if each photon only carries a third of the 18 MV energy as for my 6 MV beam, that now means I need 9 times the electron current as I do for my 18 MV beam, and that's also and 10 times is a pretty good rule of thumb for electron fluence. But the important part is to remember that the vast majority of the electrons interacting with the target produce heat. This means our target must be cooled, maybe made of something that doesn't melt readily, and so on and so forth. Here's a couple of target designs. I'm sort of showing it as in vacuum on the right and in air on the left. So if we've got a variant true beam, or if we've got a Siemens machine, say a Primus or even a Mevatron, the electron beam is here in the bending magnet, or really in the accelerating structure part, the bending magnet part of the accelerator. It is going to pass through a thin window from vacuum into air. It will begin to spread very dramatically once it hits the air. Directly below here is a canister that's got a gold or a tungsten target, and it's less than a millimeter thick. Because of this and the large amounts of heat produced, this has to be water cooled. So this entire little canister is water cooled. And because of the beam spread and the large amount of scattered electrons that are going to occur within this scheme, we have a carbon electron absorber below this, and this is almost a centimeter thick. So we have electrons exiting the vacuum, striking the target, and of course now we have a photon beam heading down the primary collimator. And a primary collimator is not always a smooth cone. Sometimes the sides are stepped, as shown on the left. If I consider the in-vacuum design, if I have a variant Linac, or if I have an Electa machine, my target is in vacuum. This is the variant approach. If I have a Linac, the Electa is on the next slide. Here I have 2 tungsten targets in a copper slug. This target itself is actually inside the vacuum chamber. So that now means I need a vacuum bellows to position the target in or out of the beam. By comparison, the in-air target is just out in air, and of course it's on a motorized slide or something to move it in and out of the beam. The electron beam strikes the target. Technically, it's still inside the bending magnetic field, and so I don't need that electron absorber. The electrons are generally swept out of the photon beam. That means my bending magnet window can be much thinner. I enter the primary collimator, and there's my cone of radiation. Now, I said that the Electa design is also a targeted vacuum. If we look at, this is essentially the same slide as earlier, I've got 2 exits to the bending magnet. One is a window. It's a nickel window, vacuum on one side, and the world is on the other. And then I've got the target. The target is a tungsten button, and it is in the other window. If I want to make photons, I merely slide this entire vacuum chamber to the left, and the beam will strike the target. If I want to make an electron beam, I slide it to the right, and the electron beam will strike the window instead. The magnetic field components are shown in yellow, remain stationary in this setup. The pink part moves. And of course, that means I need a bellows back here to accommodate that motion. So here's a photo of a Siemens style in-air target. You can see we have these cooling lines, or these silver things. The canister itself is this can. The canister itself is this circular device here. The hole here is we're looking down through the top of the can at the tungsten button. That is the tungsten button there, and you can actually see where the beam strikes it. Directly below that, contained in here, is a copper block, and then of course the beam enters here and exits the other side into the primary collimator. Here is the Varian in vacuum target. Here is the side the beam strikes. You can see there's two buttons here. This is the high energy one, and this is the low energy one. Here's the exit side, high energy, low energy. For many years, Varian had problems in that the popular failure mode here was that these would begin to leak water into the vacuum. More recently, we've been seeing targets failing per design, and that is that the electron beam eventually burns a hole in the target. And prior to water leaking into the vacuum, we begin to see changes in output, mixed photon and electron production, and so on, and that's when it's time to do a target change on our machine. So I've talked about photon production and photon efficiency. I briefly alluded to the angular distribution of X-rays from a target, but this is an important factor of how these machines work. So if I have an electron beam entering from the left here, and I have a thin target, and what thin means is a few different things. If we're talking about classical electromagnetics, a thin target is a few molecules thick. And under that condition, an electron beam entering from the left will produce a lobed sort of photon distribution, and the angle of that lobe is going to be a function of the electron energy. However, our targets cannot be just a few molecules thick. Our targets must be, usually we're talking about a millimeter of tungsten thick, and so what happens is the electron beam loses energy immediately as it enters the target. And so instead of having a single electron energy interacting and undergoing bremsstrahlung, we have many, many energies. This tends to produce an almost isotropic distribution, although it's usually somewhat lobed, depending upon energy. Now, as we increase in energy, it becomes less and less isotropic and more forward peaked. At MeV energies, it is extremely forward peaked. And I'm exaggerating with this image, of course, but the higher we go in energy, the more like a beam the X-ray distribution would appear. This creates a problem to be solved. If we want to have a uniform fluence in our photon beam, we need to deal with the fact that this is not uniform. This is not going to give us a uniform beam profile. It's going to give us a peaked beam profile. And I see that we're at our next question.
All right. Can you hear me?
I can hear you fine.
Great. Let's go ahead and get the poll started. All right, it should be loaded, and you'll go ahead and read the question. That would be great.
Okay. So which of the following is the most correct regarding bremsstrahlung target efficiency? Bremsstrahlung X-ray production is very efficient at MeV energies and requires no cooling. Target efficiency is inversely proportional and proportional to Z. At MeV energies, an overwhelming portion of the incident electrons interact to produce heat, so targets must always have some form of cooling. Or is it target efficiency is inversely proportional to Z of the target and proportional to the electron energy? I guess I made that one too easy.
Looks like some folks are still weighing in. If you just joined us and this is your first poll question, please take a moment to check the left-hand side of your screen for the poll. You can weigh in and see how others have answered this poll question, and we'll go over the answer in just a few seconds. All right, Tim, it looks like most people have had a chance to join the poll, and overwhelmingly C seems to be the answer.
Okay, well, let's go over it real quickly. Which of the following is the most correct? So is it A, Bremsstrahlung X-ray is very efficient at MeV energies, requires no cooling? No, both of those statements are false. Is it inversely proportional to the electron energy and proportional to the Z? No, it is proportional to both of those. At MeV energies, an overwhelming portion of the incident electrons interact to produce heat, so targets must always have some form of cooling. Is the correct, okay, is it target efficiency is inversely proportional to Z and proportional to electron energy? No, it is proportional to both of those. That leaves C. And yes, we are largely producing heat, overwhelmingly producing heat, as opposed to photons. And definitely have to have cooling. Otherwise, our thin target will become a few molecules thick very quickly. All right, I'm going to move forward now to the next one. We're going to talk, now I mentioned making the beam uniform, so let's talk about what we mean when we mean beam uniformity. And by beam uniformity, we mean flatness and symmetry. Flatness is the relative intensity about the central axis. Usually we apply a 3% window as defined over the central 80% of a field at a particular depth. And so F here is flatness, and it's going to be the maximum, where D is just the dose. We'll call it dose. It's not really dose, it's profile. D max minus D min over D max plus D min. And so we could draw a box over the central 80% here that would correspond to flatness. If this profile were outside this box, we would say it's not meeting that spec. Symmetry, side-to-side symmetry, usually we apply 2%. And I'm talking about areal symmetry, where we take the area on the left side and compare it to the area on the right side. And of course, if we're at 100% there, or a value of 1 over here, then we're going to be perfectly symmetric. As we deviate from that, we'll be asymmetric. Now, if I don't have a flattening filter, I have a beam profile that looks like the plots on the right. I have a dose distribution that looks like the image on the left. This is not anything like the beam profile I just showed you, and so we need some new metrics to talk about flatness and symmetry. And these are proposed from Fogliata and MedPhys. Basically, if the red line is a standard beam profile, a filtered beam profile, and the blue line is my flattening filter-free beam profile, how do I now define flatness and symmetry? The main problem, of course, here is the 50% level of this number might be very unlike the 50% level of the red line. And in fact, 50% is going to be here at B. And certainly, that's probably not something I want to use to define the width of my field here. So let's look at what Fogliata had to say. They're important features. But if we're talking about a flattening free beam profile, we're going to use a different normalization point. We're not going to use the 50% point. We're going to use the inflection point of the shoulder of the profile. This should give us a number that is consistent with the filtered beams. Our definition of penumbra will be unchanged. Our definition of unflatness is going to be at specified off-axis distances relative to the CAX. In other words, we're going to use the slope of the central third width of the half beam profile, this slope here, C to D. And we're going to look at the intercept of the two slopes to look at peak position. So these two values are in addition to flatness and symmetry to consider the qualities of a flattening filter free beam profile. And of course, each manufacturer has their own definition of what qualifies as an acceptable deviation from these for their beam profiles. And it's sort of beyond the scope of this lecture to get into that, but I thought I'd include it. Since it is part of the machine in the head. So we do want to talk about photon flattening filters. Our beam is very forward peaked, and as we go up in energy, it's more forward peaked. So that means that I need to attenuate the central part of the beam and not attenuate the beam edges so much, so I can put a conic piece of high density material in the beam and achieve that goal. The thicker it is here, the more the central axis is going to be attenuated, and less and less and less here. So For 6x, this profile here of my flattening filter may give me a flattened symmetric beam under particular conditions, whereas for 18x, it's going to take a filter this size, and these are to scale correct with respect to each other. Here's a couple of photos of some flattening filters. This one on the bottom left is 6x. The one on the right is 18x. The photography here doesn't provide for adequate comparison spatially, which is why we have this other slide. And it's also a good idea to remember that these do affect the photon spectrum, of course. The beam is going to be more hardened, passing through more material, and less hardened towards the edges of the flattening filter. Flatness is only going to be achieved under very specific conditions, and usually it is only defined usually at a depth of 10 centimeters in water at 100 centimeters SSD. And so we have to be careful when we talk about a beam being flat. We usually talk about it in relative terms, but it's important to know that if I want to change the flatness of my beam under other conditions, I'm going to have to change the shape of my flattening filter. So here's our next question.
Okay, I'm pulling it up. Let's see. Okay, so the third question should be up and running. If you'll take a moment to check for the poll question on the left-hand side of your screen and weigh in, and then we'll go over the answer. And if you'd like to just go over the question first, that would be great, Tim.
Okay, well, the question is, what is the main purpose of the photon flattening filter? Are they used to obtain a uniform spatial distribution of photon energies at a depth? Do they produce a uniform beam intensity by preferentially attenuating the forward peaked beam on the central axis and less as a function of radius away from the central axis? Are unwanted low-energy photons removed from the beam by the photon flattening filter? Or is the purpose of a photon flattening filter to produce a uniform fluence by scattering electrons? Only one of these is the most correct.
All right, if you hadn't had a chance to weigh in, we'll give everyone just a few more seconds to put their answers into the poll before we go over the correct answer. All right, Tim, looks like everyone's had a chance to weigh in on the question. I think we can go over the answers.
Okay, well, let's see. The main purpose of a photon flattening filter, and of course, two of these are deliberately ambiguous and two are silly. Is it to obtain a uniform spatial distribution of photon energies at depth? Well, no. We can't really obtain a uniform spatial distribution at any depth. This is the one that's ambiguous, of course. Is it unwanted low-energy photons are removed from the beam by the photon flattening filter? Well, some low-energy photons are removed, but that is not its main purpose. Is it to provide a uniform fluence by scattering electrons? No, that's not its primary purpose either, although that's probably going on. The main function is to correct for the fact that we have a very forward-peaked beam by preferentially attenuating on the central axis and attenuating less as we increase in radius from the central axis. All right, I'm going to move on. So once we've passed through the flattening or uniform intensity portion of the head, we're going to hit the transmission ion chamber or the dosimetry section. Now, a transmission ion chamber generally looks like a snare drum. It has an entrance window and an exit window. Of course, it's filled with a gas, possibly air. It could be sealed or open, depending upon the manufacturer. Popular materials for the windows are Kapton or Mylar, and usually we have conductors plated onto the Kapton or Mylar. Of course, it's an ion chamber, so incident electrons and photons interact with the gas inside, cause ionization. We have a bias voltage present. This causes the liberated charges to migrate to one electrode or the other. We can then measure that migration as charge or dose external to the device. Here is sort of a profile of a segmented ion chamber. The nice thing about a transmission ion chamber is we can use it to both measure the beam in terms of dose, but we can also use it to monitor the beam shape. If I have several different electrodes that the beam is passing through, such as A and B and C and D here, each of them is intercepted by a different portion of the beam, and if the beam is asymmetric or unflat, they will record different values. So I can perhaps take the sum of A and B and say, okay, that's dose. I'm going to monitor that and say that's dose. I can take the difference between A and B and say, okay, this is probably going to tell me something about the beam position with respect to where it should be. And if I look at the difference between what's on C and what's on D, by which I mean current or charge on C and D, that might tell me something about the angle at which the beam is passing through. And so then I can use these different signals or these error signals to either drive the beam back into position with steering or even generate an interlock if it exceeds some value. And usually, of course, on these systems, we have two ion chambers. They're in series. The beam passes first through one and then the other. And so I would have one chamber with these segments oriented as shown, and the second one, they would be oriented, rotated 90 degrees from this one. Here is a couple of photos of a segmented ion chamber. This one happens to be out of an old Saturn 43 machine. But so you can see here, there's a central collecting electrode, and it's got a segment around it, and then it's got some other segments outside of it. So in this case, they have a circular central electrode. That one's going to be dose, and what they might be doing here is looking at the difference between this one and the outer electrodes in order to get clues about the beam profile. Of course, we've peeled away the outside plate here, and you can see that it's kapton on the outside and alumina on the inside. Here's the other side of this chamber up here on the right, and it only has a minor tear in it. If I have a variant machine, the pattern of the segments looks a lot more like the previous slide, where I've got two hemicircles and then I've got some outer segments. This part here is going to be a guard electrode. It's going to help keep fringe fields at the edges of these of the bias field from interfering with electron transport between the plates and the ionizations. So that's it for transmission ion chambers and beam monitor. I'm now going to talk very quickly about photon block collimation. Someone asked about whether I'm referring here to the secondary collimator. And yes, this is generally be referred to as the secondary collimator. So as I said earlier, the field defining edge of the collimator must be parallel to ray line projected from the source. So the blocks must move at a tangent to the radius. This takes up a lot of space in the head of the machine. So, you know, if this block has to move, and if you notice, it's we can look at the amount of space occupied by this top corner as we move the block. We can see it really needs quite a lot of vertical room. So if I double that, I have a lot of room. One way to save space, some of my older Siemens machines have this, is that we have the face of the block pivot as it moves, and this allows the entire block to move in a plane rather than taking a curved path, and so saving a significant space. And this is a fairly recent development. If you have Siemens machines, if you've got Siemens Primus, you probably have this type of collimator, at least for one set of jaws. Here's a photo of an upper set of jaws from a Varian machine with the lower jaws removed and the MLC removed. And so the way these work is this is a regular block style, and so that means the jaw has to travel in a curved path. And so it travels on this track, which is curved. It's sort of arch-shaped. Of course, the collimators don't have to be block-shaped. If I have a more recent Electa Versa HD machine, if I have their agility MLC, my diaphragms, as they call them, or backup jaws, the pair of block jaws in the machine, are actually triangular in shape. And this reduces the weight that has to be carried and takes advantage of the fact that we rarely need to collimate both in this region and this region simultaneously. Of course, most modern machines are equipped with multi-leaf collimators, so that we don't have just rectangular field shapes. And on the left, I've got sort of an overlaid image from a treatment planning system on an X-ray. I have down here a portal image showing the stepped edge that's produced by an MLC, but we have that same general shape. And on the right is a photo courtesy of Varian showing an MLC making a shaped field. So characteristics of multi-leaf collimators. Popular today are what we call single focus MLCs. The leaf ends are rounded. This gives us a wider penumbra than if the leaf ends are flat and move in an arc, but it gives us a constant penumbra because about the same amount of leaf end is always transmitted by the beam edge. Double focus MLC, each leaf would have to move in an arc as with the old style blocks. This has some problems in terms of drivetrain and taking up space. So I don't know that anyone's using this approach anymore. Most MLCs have some sort of tongue and groove construction to prevent photons from just passing between the leaves. And we don't want hot spots or hot lines showing up. And even with tongue and groove, we do see streak artifacts from time to time. Most modern MLCs use some sort of carriage or leaf guide structure to move the entire bank of leaves and then have the leaves extend and retract from it. So this is a representation of those in a top view and then in a side view. Here's a photo of a going way back in time Varian Mark style MLC leaf. And so you can see here's the curved leaf end, here's the actual leaf blocking part itself, and of course this section back here on the left would not be extended into the beam. And you can see the tongue and groove structure here. Here's question 4.
All right, question 4 is up. So go ahead and take a moment to answer it on the left-hand side of your screen, and we will take about a minute to let everyone weigh in before we go over the answer. Tim, would you like to go over the question?
Sure thing. So we mentioned beam penumbra and sharpness of a beam edge. So what is critical about a photon collimator with regard to beam penumbra or the beam edge? Is it critical that for minimal and consistent penumbra, it is necessary for the collimating surface to be parallel to ray lines projected from the source? Is it critical that focal collimators have cupped collimating surfaces to prevent a curved trajectory? Is it critical that photon collimation is always kept close to the patient for penumbra control? Or is it critical that photon scatter in air requires that collimating surfaces be non-skid?
All right, if you hadn't had a chance to weigh in on the poll question, now's your opportunity to do so. And once everyone has a chance to put their questions in, we'll go over the answer. We'll give everyone just a few more seconds to do that. All right, Tim, it looks like most people have had a chance to put their poll answers in, so you can go ahead and go over the answers.
All right, let's go then. And as before, 2 of them are silly, and of course 1 is correct, and then 1 is slightly ambiguous. So, Focal collimators have cupped collimating surfaces to permit curved trajectory. That's not it. Photon collimation is always kept close to the patient for penumbra control. Not true. That's the ambiguous one. Yes, the closer it is to the patient, the smaller the penumbra will be, but we cannot use the word always there. Photon scatter in air requires collimating surfaces be non-skid. Well, that's silly. So for minimal and consistent penumbra, it is necessary for the collimating surface to be parallel to ray lines projected from the source. And so this applies specifically to block collimators. Of course, in the case of an MLC with a curved leaf end, we are sacrificing the penumbra width for a consistent but much wider penumbra. Okay, I'm going to move along then. Photon beam misalignment. So earlier I said, some parts of the beam are more sensitive to misalignment of angle versus position. So if I have an electron beam incident on a target, so here's a target, a target, a target. Here is primary collimator. This red blob is my a photon beam coming off of the target. The flattening filter is this blue thing, and here's my beam profile. Now, if the flattening filter and electron beam and target and central axis are all aligned, I get a lovely flat and symmetric beam profile. What if they're not? So if my electron beam is at an incorrect angle, a portion of my cone of radiation is going to be intercepted both by the primary collimator and the flattening filter. And of course, I'm greatly exaggerating this here. This tends to produce a sloped profile. The profile is going to be sloped, and that means that the outer edges of the beam, or the outer edges of my transmission ion chamber, are more sensitive to angle offset than the central portion. By comparison, if I have a position offset of my electron beam, as shown on the right, I will have an uneven slope. I'll have sort of a discontinuity in the middle of my beam profile. When I see this, I know I have a position error to adjust. And that's why the central portion of my ion chamber is used for position adjustment. And of course, if I have beam steering, I can steer this thing back into place. Or if not, then I have to move the flattening filter around in order to achieve proper alignment. So I'd like to talk briefly about electronic beam steering compared to shoving flattening filters around. And of course, this brings us back to motion in a dipole magnetic field. So if I have an electron in a magnetic field, it's going to tend to curve if it has some velocity that is perpendicular to the magnetic field. So that means I can replace the poles of my magnet shown here on the left with electromagnet coils or a pair of electromagnets, and so produce a nice field in between there where my electron is going to pass through. So now when my electron beam passes between my pair of coils, I can bend that beam perpendicular to the coils, perpendicular to the axis of the coils. So if I want to do beam steering, where am I going to put the pairs of coils? Each of these little yellow cylinders corresponds to a coil. So here's a coil pair that's vertically oriented. There's a coil pair going in and out of the page, shown as a circle here. There's another set of 4 coils here at the end of the accelerator. Here's a set of coils in the bending magnet. Here's a set of coils entering the bending magnet. Of course, this looks a lot like a variant Linac. Well, okay. The radial plane is the plane formed by the beam through the bends, the accelerator, and the bending magnet. So the radial plane is going to be parallel to the page here. The transverse plane, also known as cross plane or the AB plane, is the plane that is perpendicular to the page here, or in and out of the page. And by putting different current values on each of these magnets, I can control first the position of the beam in the accelerator, the position of the beam as it leaves the accelerator, or the angle of the beam as it's leaving the bending magnet. Angle coils are almost always in the bending magnet. Position coils are usually prior to the bending magnet. Now we're going to talk about a clinical electron beam head. Here's that slide to remind us all that we no longer have a flattening filter, and we still have a dose monitor. We might have block collimators, but they're going to be pushed out of the way. We have electron collimation, which must be multi-level and close to the patient. So let's go first to the dual foil scattering, which is our method of flattening the beam. Most of our modern linear accelerators that are used in medicine use dual foil scattering. Dual foil scattering is two sets of foils placed in the beam. The first foil is usually higher Z relative to the second foil. It spreads the beam out. Okay, it gives us some beam spread. The second foil is usually shaped and is usually a low Z material, often aluminum, and it will often have a wedding cake shape. It behaves almost like a flattening filter in a photon beam, but these work primarily by scattering, whereas for a photon beam, a flattening filter works primarily through absorption. Incidentally, if I have a dual foil scattering system for my electrons, my virtual source is likely to locate somewhere between the two foils. It is often not corresponding to the window, even though the window is the source. Now, these foils being in the beam do produce some photon contamination. They act as targets. We get some bremsstrahlung occurring here. And there's another way to deal with that. But first, let's look at some pictures of some scattering foils. These are both secondary foils. They're out of that same CGR Saturn 43 machine that we looked at the ion chamber from earlier. And this is to illustrate the wedding cake design. You can see we've got several layers of aluminum foil here, but clearly the structure is different in terms of how these pieces are stacked. So this is two different energies. And as I said, we get some bremsstrahlung from these guys, but there is a way to get a non-bremsstrahlung electron beam uniform, and that'll be in the next slide. Here's a Varian dual scattering foil assembly. This is both foils in one device. This is the upper foil here, and then the lower foil is in the background here, also shown here. You can see both of these are sandwiches of different materials. The lower foil does have that wedding cake shape. It's just enveloped between some layers of aluminum. So if I want to have a no bremsstrahlung electron beam, I don't use foils to scatter the beam. I use electromagnetic steering to form a raster pattern. And what I have is two pairs of coils with the beam passing between them. And I have a swept current flowing through the coils. I have this sawtooth shape. If I plot the current going through the coils to produce the magnetic field, it's going to be a sawtooth. It's going to increase and increase and increase, and then drop to minimum. Increase, 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 drop to minimum. This is going to produce a sweep and return of the electron beam perpendicular to that magnetic field. So if I have two pairs of coils and I operate them at two different sawtooth frequencies, I can produce a raster scan, much like in the old video tube type televisions we used to have. And in fact, it's exactly the same technology. This arrangement of coils would be called a yoke. And I feed two different sawtooths to each pair, a different sawtooth to each pair of coils, and I get a raster pattern that sweeps through and returns and sweeps through and returns. The upside is there's little or no X-rays added. The downside is we have to make sure that these remain random with each other. We have to provide them. They have to be accurate. The downside is if this fails, this is an extremely high fluence electron beam, because the fluence of this beam has to give us our desired dose rate spread out over a 40 by 40 field. So that now means that the instantaneous dose rate of this 1 centimeter wide beam is going to be several thousand mu per minute or centigrade per minute. And so the complication and the risk sort of negate the benefit in many cases. I don't know that any manufacturers are using this for medical electron Linacs. I had said that electron beams need multiple layers of collimation. Here are two different electron collimators just to illustrate the three levels. So here's one level, and of course these slide into a tray at the bottom of the head. This one latches up, but this part connects to the head of the machine, and we have 1, 2, 3 layers of collimation. Of course, this bottom layer is very close to the patient. And if I want a non-square or non-rectangular field, I need to make a custom molded collimator to go in the bottom of this. And so Here's one on the left for the applicator on the left, and here's one on the right for the applicator on the right, just to have a couple of examples to look at. So here's question 5.
Okay, great. You can go ahead and answer the poll on the left-hand side of your screen. This will be our last poll question for the evening, so make sure to join in and give an answer, and then we will go over all of the answers in just a moment. Tim, you can go over the question if you'd like.
Okay, which of the following is most correct regarding electron beam shaping? Electrons scatter readily in air, necessitating multiple levels of collimation with the most distal aperture close to the patient surface. Or is it because electrons scatter in air, the final level of electron collimation must be in vacuum? Or is it that, unlike photons, electrons do not scatter readily in air, therefore multiple levels of collimation are necessary but can be contained in the treatment head? Or is it because electron beams tend to exhibit a Gaussian profile, no collimation is needed if the treatment planning system uses a Monte Carlo algorithm?
All right, let's just give everyone a few moments to answer this last poll question. If you haven't had a chance to do so already, it should be on the left-hand side of your screen. You can go ahead and weigh in, and we will go over the answer in just a moment. All right, Tim, it looks like everyone's had a chance to answer the question. I think we can go over the answers.
Okay, great. So which of the following is most correct regarding electron collimation? Is it because electrons scatter in air, the final level must be in vacuum? No. And it is also not, unlike photons, electrons do not scatter readily in air. That is false. Therefore, multiple levels of collimation are necessary but can be contained in the treatment head. Well, the first part's false. D, electron beams tend to exhibit a Gaussian profile. That's true. But having a Monte Carlo treatment planning system isn't going to collimate the beam for me. The correct answer is A. I think I said it a few times. Electrons scatter very readily in air. And so that means that if my beam is going to be anything but Gaussian at the patient, I'm going to have to collimate it over and over and close to the patient. I have a few more slides to cover, but that's the last question. And so let's go. So it said at the beginning I would cover head leakage. I draw this picture of an accelerator and an accelerator head as though everything's neat and tidy. But the reality is that when we produce an electron or a photon beam, there's scatter occurring everywhere. And if we were to shut the jaws of the machine so that the useful beam can't exit the head, without a lot of shielding, we would measure quite a large fluence of electrons and photons in the room. And this, of course, contributes to the patient's total body dose. So it is important that we limit this. Basically, everything the beam hits produces scatter, either photons or electrons, and it's more or less isotropic. And the regulatory limit for this, in general, is 0.1% of the dose-rated isocenter. Now, 0.1%, if we're going to make a shield that's going to only transmit 0.1%, that's right at about 10 half-value layers. So there's quite a lot of shielding in the heads of these machines. So if I'm commissioning a machine and I need to figure out what the head leakage is, there are two ways I can go about it. I can accept the manufacturer's statement that it's less than 0.1% and assume that the machine was built perfectly in the factory. Or I can go ahead and measure it. And the measurement technique is as follows. First, I map the field by covering the treatment head in films and exposing them. Here's a picture of a Versa HD with most of the head covered with films. Notice that each film has a number and an orientation mark, because once I have exposed this with the jaws closed and running many thousands of monitor units, I am then going to process these and return them to the head in the same locations. And I'm going to look at the hotspots that show up, and then I'm going to use an ion chamber that I've cross-calibrated to the dose-rated isocenter in order to measure the exposure levels at usually 1 meter from these hotspots. So there's the films. Now there's the mapped field, and you can see we've got 3 hotspots. These correspond roughly to where the 3 bends are in the slalom bending magnet. So what I'm going to do is I'm going to take my ion chamber with a buildup cap, which I have cross-calibrated with the dose at isocenter. I'm just going to put it near each of these and measure the exposure rate here, and then estimate what it's going to be at a meter from there. And hopefully they're going to be less than 0.1%. I don't recall the exact value I got in this case, but it was well below that regulatory limit. The other sort of not quite inside the Linac thing we said I would talk about here is wedges. And I'm going to go ahead and go. So, and the reason this gets covered as part of the Linac talk is because, as you'll see in a couple of slides, sometimes that wedge is actually inside the treatment head. So sometimes it's dosimetrically convenient to produce a tilted beam profile, usually to compensate for the shape of the patient or to obtain a uniform dose where 2 beams intersect. Historically, we do this by placing a wedge-shaped attenuator in the beam. Historically, this is something mounted on a tray that gets put in the bottom of the head, and it produces this nice tilted beam profile, like in the plot on the right. Of course, the pink thing is the wedge filter, as we used to call them. So here is a sketch of a single isodose line, and of course the wedge angle is defined as the angle that one of the isodose lines makes as it passes through the central axis at a particular depth, usually 10 centimeters. And so it's this angle here, theta, what we would call the wedge angle for a field for a 10 by 10 at a depth of 10. Typically, machines were equipped with several filters at usually 15, 30, 45, and 60-degree wedge angles. It's a good idea to remember that, like flattening filters, wedges affect the photon spectrum. And so if I look at the way the beam profile changes with depth for my wedged beam, even if I'm in the unwedged direction profile, I will see that the behavior as the profile changes with depth is quite different than for the unwedged beam, and this is because the presence of the filter alters the photon spectrum. Here's a photo of a physical wedge. This one's off of one of my Siemens machines. This is the 60-degree wedge. It's sort of a universal wedge. Here's a shot hoping to allow you to see that, in fact, yes, it's a wedge-shaped piece of metal that we're putting in the beam. So another form of technology with which we obtain wedge-shaped profiles is through what we call a motorized wedge. We can just have a smaller wedge up inside the head of the machine that is the highest wedge angle we might want, say 60 degrees. And we can put that in the beam some of the time and then have an open beam delivery the rest of the time and use something called the ratio of tangents to obtain any beam angle we want up to the angle that corresponds to the wedge that we have in place. So we just deliver some radiation with an open beam, and we deliver some radiation with the wedge in place, and the beam weighting we need to get a particular wedge angle is shown by this formula here, where theta sub e is the angle we would get with the physical wedge in place, and theta sub w is the physical wedge, theta sub e is the desired effective wedge angle, and b is the relative weighting of the open and wedged field. Another way to obtain wedge distributions is what's called a dynamic wedge. Here we just move one of the photon jaws sequentially as we deliver the beam, and I have I don't think a very good quality profile here on the right. As I move this jaw and deliver some beam, you can see that basically what I'm doing is I'm superimposing wider and wider or smaller and smaller jaw openings upon each other in order to produce a wedge distribution. The set of ordered pairs of monitor units in jaw position that produces this is the simplest form of what's called a segmented treatment table. Of course, today we're doing IMRT and VMAT, and so a true full segmented treatment table would also contain the gantry angle, the collimator angle, the couch position, basically all the machine parameters are contained in a segmented treatment table. Recalling our last slide, though, for a dynamic wedge, we really only need to store a single STT wedge table for each photon energy, and then use ratio of tangents method to deliver other wedge angle profiles by weighting open and wedged beams. So what I would do is I would simply deliver more beam with the jaws fully open in order to reduce this wedge angle to something, say, 30 degrees or 15 degrees. So that's the three kinds of wedges. Here are my references for this talk. Specific ones that I referred to are used. And here are some references that you may find useful if you're preparing for the boards. I like these because they're free and they really cover accelerators in depth. Thank you all for listening. I hope you found this useful and informative, and good night, I guess.
Well, before you go, Tim, maybe we can take a moment.
I'm not going anywhere yet. I'm happy to stay.
Well, thank you so much for that presentation, and thank you all for joining us. And I want to take a moment. If there are any unaddressed questions in the chat, now would be a good time to answer them. And if anyone else has questions, we can take just a couple moments to go over those. I don't know if there are any that you didn't get a chance to address, Tim, but now would be a good time to do that.
So one question, so there are two I recall. Everyone, please understand, while I'm presenting, I don't get to see the chat. So I really only had a chance to look at it while the polls were going on. There was a question about whether we call the block collimators the secondary collimators. Yes, strictly speaking, they are often called secondary collimators, whereas what I was referring to as the primary collimator is the primary collimator. There was also a question about comparing a 270-degree bending magnet to the slalom bending magnet. Electa would tell you that the slalom bending magnet occupies less vertical space than the classic Varian 270-degree bending magnet, and that is true. Electa would also tell you that the total beam emittance is less with the slalom magnet because the beam is bent through fewer degrees of bend, and that is also true. I would argue that the first argument is much more important than the second argument. If we were talking about a particle accelerator where we had a synchrotron or a cyclotron, beam emittance is extremely important. The way that we manage the beams in medical electron Linacs, it's not that big a deal. If I have a Varian true beam, that also has a shorter vertical profile, and that's covered in lecture 1, so I'm going to leave that alone. There was, let's see, okay, so how would you numerically obtain the wedge angle? Are you referring, so in the case of the ratio of tangents, I use a physical wedge. I can apply the same ratio of tangents to the dynamic wedge, which is what I assume you're referring to, Ahmed. And so there, what I would have is I would have an STT table for a 60-degree wedge, and I would use that same ratio of tangents to combine the 60-degree dynamic wedge with open fields to obtain other wedge angles. I hope that's clear. And so far, I think that's it for unanswered questions. Still trying to read through these quickly. Yeah, it looks like the bending magnet one. Oh, okay, steel over lead for the primary collimator. Steel is actually easier to machine than lead, and it also holds its shape well. It's also non-toxic. Lead also gets activated over time. I mean, there's a few reasons. From a manufacturing perspective, the machinability of steel would trump the whole thing. Okay, I think that's all the questions that I can find quickly.
All right.
Oh,
Well,
okay.
you find another one?
One more, sorry. So
No, that's
Steve,
fine.
um, if we can talk about it, but that was covered in detail in the first lecture. If you think about what I said earlier, and that is that the really the beam energy depends upon the amount of RF power in each cavity, and there's lots of engineering solutions to solving that problem. Depending upon whether I have a standing wave or a traveling wave accelerator, the simplest method is to control the amount of RF power going into the accelerator. There's a few other ways, and probably ought not to spend that much time on it here.
Okay, well,
I
thank
think
you.
that's about it.
Thank you again, Tim.
My pleasure.
And thank you all for joining us for this free event hosted by WePast. And you can join us for the next free webinar in the series, which will be Therapy Room Shielding using NCRP 151 on Wednesday, February 22nd at 6:30 p.m. Eastern Time with speaker Jim Rogers, the Director of Physics for the CyberKnife at MedStar Franklin Square Hospital. And for up-to-date information about upcoming webinars, you can follow WePast on Facebook, Twitter, and Google+. If you'd like to make a recommendation for a future speaker, you can contact me directly via email at christina@wepass.com, or you can take this short survey. Thank you so much, and good night.